And we are very glad to have Alberto. Alberto is a PhD student in our group, and I'm a supervisor, in fact, so I'm very glad to introduce him. Alberto is a bachelor and master in philosophy from San Raffaele University here in Milan, after which he moved to our PhD program. He has been visiting at the Institute for Artificial Intelligence at the University of in Lugano, at the always get confused, University of Italian Switzerland, or whatever the combination of work that will be here. So Istituto dalle Molli di Studi sull'Intelligenza Artificiale, and he has entered this last year of his PhD. Now is in his writing phase, and during the last couple of years he has been able already to contribute to several conferences. So today he will present some of the work that he concluded during these first 2 years of his PhD. Is joint work with myself and colleagues from the Istituto dalle Molle in Lugano, so model checking stochastic multi-agent system with imprecise probabilities. Alberto, the floor is yours, and as usual, we will have the 40-45 minutes talk, followed by some time for discussion.
Thank you, Giuseppe, for the kind introduction. As Giuseppe already mentioned, today I'm presenting this work that is a joint work between me, Giuseppe, and Alessandro Antonucci, Alessandro Facchini, researchers at the Dalle Molle Institute of Artificial Intelligence. The content of this presentation is related to a paper that we submitted approximately 1 month ago, and it is now under review, and it has been already presented in 2 conferences, EUMAS last year and EIPCTL. So this is the result of 1 year of research that I spent at Dalle Molle Institute in Lugano, and it's still also a part of my PhD thesis, one of the chapter of my PhD thesis. I decided for today to do a sort of broad introduction to the topic, presupposing that we have also people that is not really acquainted with model checking. Then what I'm going to do is a short introduction to the field of model checking and probabilistic model checking, and then pass to present our work. So really briefly, model checking is a field of computer science that includes several kind of logic-inspired methods and techniques to check whether the design of computational systems satisfies given desirable properties. Okay, for instance, let's suppose to have a system like the system M depicted in the figure. This system has 4 possible states and evolves across time, shifting its states from start to try, lost, and deliver. This is an example of a system for sending messages, of course. We can model computational systems behavior of systems like system M using structures that are analogous to those introduced by Soltripti for modeling the semantics of model logic. That is to say, we can have a structure composed by a set of possible words. Here, possible words are in fact the possible states of our computational system, with the additional constraint that the set of possible states is finite and non-empty, because remember, we are modeling the states of a system. So we are using cryptic structures to model something real specific and physically grounded. Also, instead of having the classical accessibility relation, we have a transition relation that represents the possible transitions between different states of the system. And instead of the classical evaluation function, we have a labeling function that takes labels from a finite collections of labels that represent atomic properties of the system and label the various state of the system. For instance, here in the example, the labeling function label the first state with start, the second with try, the third with lost, and the fourth with delivered. Okay, and the transitions are represented here by arrows. So as you see, the basic semantic condition that we use is to say that a certain atomic property, such as lost, holds in a certain state of the system if and only if the labeling function assigns that labels to the state. For instance, in this example, our model of the system and the state lost satisfies the atomic property lost because the labeling function assigns to the state lost the label lost. So it's really a simple trick to connect logic with state transition systems. So as we in the same way we use cryptic structures to model the behavior of our computational systems, we can use model languages and extensions of model languages to model our desirable requirements. For instance, we can have, as an example, sorry, there's a mistake here, but a desirable requirement can be that it is not possible that the system lose the message, and we can model this requirement using the standard possibility operators. Of course, there is a negation here that I missed, but saying that it's not possible that property lost, and this model formula has to be satisfied by the initial state of the system in the system. Okay, so this is the usual way model checking operates. We have cryptic style structures to model the behavior for the systems. We use model languages to model desirable requirements, and then we provide semantics to give conditions under which we know that the desirable requirements are satisfied by the model of the system. Okay. And finally, what we do is to create algorithms that compute these satisfiability conditions and check whether exactly, for instance, in the example, the model M in the state star satisfies this property in a fully automatic way. It's a method, as you can see, to verify that our models, our systems behave in the way we want they behave. Okay, so it's a verification method properly. Okay, in the initial example, I introduced a standard computational systems. The interesting advancement of the subfield of model checking, that is probabilistic model checking, is that we can describe in a finer way the behavior of stochastic computational systems using a particular specification of the initial structures presented, in which we have not only the transitions, but we label the transitions with parameters included in the norm 0, 1 that represents the probability to that the transition occurs. So, for instance, in the example here we have that the transition from start to try has probability 1 to occurs, and the same for the transition between delivered and start. Instead, the probability from try to lost and the probability from try to delivered are respectively 0.1 and 0.9. Okay, in a compact way, we can describe these transition probabilities between states of our system using a transition matrix that assigns for each pair of states in the Cartesian product of the set of states of the system, the probability to reach the second state from the first state in one time step. So the behavior of the system is a behavior across time. At each time step, the system changes the state, and the transition matrix provides us the transition probabilities in one time step. Of course, in using this formalism, we are introducing two really important assumptions that are limiting assumptions, so assumptions that limit the kinds of systems we can model through this formalism. These assumptions are the stationarity assumption, that is to say that the stochastic behavior of the system does not change across time, namely the probability of the system to shift from state S t and another state as t plus 1 from time t to time t plus 1 is the same independently from the time. So independently from the time we look, our system M has always a probability 1 to shift from start to try, and so on and so forth. The other assumption is the so-called Markov condition that corresponds to assume that our system is memoryless. So the probability of each transition is totally independent from all the transitions occurred before, in the time before. So the probability to shift from start to try at a certain time step t is the same and independent from all the transitions occurred before. Okay. Given these assumptions and given the structure that I introduced, it's clear that our system M behaves as a well-known kind of stochastic process that is a discrete time Markov chain. In fact, in probabilistic model checking, our models that we use to describe the behavior of systems are, in fact, a specific kind of discrete time Markov chains that are labeled discrete time Markov chains, where a labeled discrete time Markov chain is a tuple composed by a set of states, a transition matrix that describes the probability, a transition probability between states of the model, a set, a finite non-empty set of labels, and a labeling function. Okay? Okay. Over these models, we define a new language that is a modal language called the Probabilistic Computational Tree Logic, Probabilistic Computation Tree Logic, sorry. And this language has a strange, specific model operator that we use to model interesting, desirable properties of our systems. The language includes two kinds of formula, phi formula and psi formula, phi formula and psi formula. Phi formula can be the true, so top, atoms, negations, conjunctions, and then we have this particular kind of formula that is probabilistic formula, and this kind of formula means the probability to reach a path that satisfies psi is less or equal or greater than b. Okay, hence we have psi formula. Psi formulae are used to represent properties of paths, namely possible evolutions across time of our system. So our systems has a stochastic behavior, and so there are many different possible evolutions of the system across time, and each one of these evolution is a path, and properties of path are modeled by these three kind of formula. The first one means in the next state of the path phi holds. The second one means phi 1 holds along the path until phi 2 holds. And the third one means phi 1 holds along the path until time step t and phi 2 holds. Okay, as you see, the probabilistic operators, what the probabilistic operator does is to quantify probabilities across over paths. So it says how many paths satisfy among the paths outgoing from a certain state satisfy the formula specified in the operator, in the scope of the operator. Okay. Those formulae are provided with a well-defined semantics that is where the satisfiability conditions are defined with respect to a discrete Markov chain, and the state. For the Boolean formula, the semantics is the same than in standard Boolean logic. Instead, for the new operators, we have a specific semantics where the probability, the formula saying that the probability to reach a path that satisfies psi is less equal greater than b is satisfied in a state S of the model if and only if there is in fact a probability less equal greater than b that a path is reached from state S. Sorry, one thing that I missed to say, notice that this symbol, the knowable symbol, is a short way to write less equal greater than. When we specify the formula, in fact, we replace this meta symbol with a specific symbol representing the interval of probability that we want to specify. Okay, for what concerns path formula, remember that, as I said, paths represent possible evolutions of our systems. So we can see a path as a function that assigns at each time t a state that represents the actual state of the system at that time. And here we denote values of pi by pi 0, pi 1, and so on. So the semantics of psi is given with respect to our model and the path pi, and the conditions are the following. In the next state of the path phi holds if and only if effectively in the state phi 1, that is the first state of the path after the initial state, phi holds. Phi 1 holds until time step t, then phi 2 holds if and only if there exists a tau less equal than t that satisfies these conditions, and the same for until formula. Okay, the interesting thing that we want to do here is to look at the algorithms that allow us to compute using the satisfiability conditions that I have presented. Let's say whether a certain state of the model describing the behavior for a system satisfy a formula that describes, that specifies the desirable requirement that we want the model satisfy, the system satisfies. So the algorithm proceeds in this way, denote by sat phi the set of all states that satisfy a certain formula phi, and we can compute sat of the specific phi formula using the simple equations. So the sat of top is the whole set of states. The set of atom P is the set of all the states that are labeled by P. the SAT of a conjunction of phi1 and phi2 is the intersection of SAT phi1 and SAT phi2. The SAT of a negation is the complement, and this is the only interesting inference in standard model checking, the SAT of a formula with a probability operator requires to compute for each S in S, to check for each S in S whether the probability that a path satisfying psi is reached from S is effectively satisfy the threshold specified here. So, as I said, now the non-trivial step is the computation of this probability. We use to compute this probability the transition matrix that is provided with the specification of the model, and the procedure varies depending on the nature of the formula psi. When our formula is next phi, we compute this probability simply as the sum for each state S prime in SAT phi. So for each, we look at each state that satisfy formula phi, and we compute, we make the sum on all the transitions. Things are a little bit more complicated if we look at eating probability. If we look at, until and bounded until formula. So when psi is a formula of the kind phi1 until phi2 and or phi1 until times t phi2. When we have this kind of formula, we compute our probability as an eating probability. Eating probability is a standard kind of inference that is usually done on computed over discrete Markov chains. And in particular, given a discrete Markov chain, a state and S and an event B, where an event is a subset of the set of states, we call eating probability of the event B with respect to S, denoted with this notation, the probability of our system to reach B from S eventually in the future. This probability can be obtained in time polynomial in the number of states of the model, following computing the minimal solutions of the following system of linear equations. And this operation can be done, as I said, in time polynomial in the number of states through usually linear programming and solving a linear programming task. There are also other methods based on dynamic programming, but okay, I skip the details because they are not so relevant here. Instead, when our formula psi is a formula of the kind phi1 until times t2, this probability corresponds to the so-called eating probability of the event SAT phi2. So the second event here. Combinatorial the modified transition matrix T, which is obtained from the initial transition matrix, making all the states S1 absorb in S absorbing, excluding those in the complement of set phi1 with respect to set phi2. This is a strategy, in fact, because we want to that at a certain point phi2 holds, and in all the previous state phi1 holds. So this is modifying the matrix is a strategy to force all the states before phi2 to satisfy phi1. So we consider in the transitions only the transitions that pass through states that satisfy phi1 and at the end reach a state that satisfies phi2. Okay.
Alberto, sorry, Alberto.
Yeah.
Maybe worth saying a few words about absorbing states.
Okay, yeah, of course. an absorbing state is a state, so in a user description, an absorbing state is a state such that there is a probability 1 of transiting from that state to the same state and 0 for all the other states. So an absorbing state is a state where when you are in that state, you cannot exit the state. So you remain in the same state indefinitely. Okay. It's a final state of the process. So it represents a point of end. Okay. In recent years, the formalism of standard probabilistic model checking, which is conceived to model properties mainly of computational systems composed by one single agent, has extended to deal with multi-agent systems. And in particular, in those two works that I mentioned here, it has extended to deal with epistemic stochastic multi-agent systems. The framework used is that of probabilistic interpreted systems. Probabilistic interpreted systems are a particular kind of structure that is obtained extending to multi-agent systems the formalism of Markov's chain that I've already just presented and introduced. A probabilistic interpreted system is usually defined as a tuple that is composed by a finite non-empty set of global states of the multi-agent system. Here I highlighted the word global states because usually in a multi-agent system we have to distinguish between local states that are the single states of a single agent in the system and a global state that represents the state of the whole multi-agent system at a certain time. Here we assume, as is done in the work that I cited, we assume directly global state as primitive, but it's also common in probabilistic interpreted systems to define global state as tuple composed by the local state of the single agent. So global state is a tuple of local states where each local state represents the state of one agent in the system at a specific time. Okay, just to be clear here. Also in this structure, we have a finite and empty set of agents that are all the agents included in the system. And we have, instead of a single transition matrix, a family of transition matrices, one for each agent in the system. And each transition matrix describes the stochastic behavior of one single agent. Furthermore, to model epistemic properties, we introduce a family of epistemic equivalent relations. Again, one equivalent relations for each agent in the system. A finite set of labels, which are used to represent atomic properties, and a labeling function. Okay, as you can see here, this is an extension of Markov chain to multi-agent systems, to model multi-agent systems. Okay, over the structures.
Alberto, if I may again, maybe just to mention that here the term agent does not always refer to rational agents in the way epistemic logic does. But if you want to say a few words, maybe it's worth.
Of course, we are using here the term agents in the standard use that is done in computer science as computational agents. So an agent is a computational system, a machines that compute a certain function. So we are not assuming agents as subjects or epistemic subjects. They can be also standard computational systems, okay? So in fact, our multi-agent system is a computational system made by different sub-computational systems that are...
Yeah, typically they are components of the system, yes.
Or component of the system, in fact. Okay. In probabilistic model checking for multi-agent systems, there is a language to specify properties is the logic PCTL-K. PCTL-K is an extension of PCTL that we presented before, where we have the same operators of PCTL with, in addition, some operators to model epistemic properties. We have the standard knowledge operator, and then we have these three operators to represent knowledge in groups of agents. In particular, everybody knows common knowledge and distributed. Here there is a mistake. Distributed knowledge is T gamma. Okay, these are different kinds of knowledge that I'm going to clarify better in the semantics. Okay. The semantics for knowledge is the standard semantics interpreted systems. So we have phi, agent I knows formula phi in a certain state, if and only if. Phi holds in all the states that are accessible or equivalent in this formalism to our initial state. The same condition is introduced for everybody knows common knowledge and distributed knowledge, but introducing specific epistemic equivalence relations for a group of agents. In particular, the equivalence relations for everybody knows is simply the union set of all the equivalence relations for all the agents. That for common knowledge is the iterative closure of the union, and that for distributed knowledge is the intersection. Okay. For what concerns the model checking algorithms, we have the same. Of course, we have a model checking part for the epistemic operator that is standard. I skip it because to stay in time. And for what concerns the probabilistic inferences, the model checking algorithms are the same as in standard PCTL, with the only difference that we replace the standard transition matrix with a new global transition matrix that describes the overall stochastic behavior of the whole multi-agent system, and that is computing for each S prime, the so-called logarithmic pooling that is done here, where this factor is a normalizing factor. Okay. As I said, once defined this new global transition matrix, the relevant probabilistic model checking tasks are analogous to those in standard PCTL. Okay. Now let me go to the new part. So there are some issues related to the use of probabilistic interpreted system, both for single multi-agent systems, and these issues are related to the two assumptions that I mentioned before, really to one of the two assumptions, that is the stationarity assumption. So given the stationarity assumption, we cannot model non-stationary stochastic agents whose transition probabilities vary across time, and also we cannot model high-order uncertainty about probabilities. So we require that all the transitions probability are known and specified in the model. There exist some solutions for these issues, and in particular those based on the use of parametric Markov models, but those solutions generally comport exponential complexity in the number of states of the models. So they are not really computationally feasible solutions. Exactly starting from this, our idea is why don't we use imprecise probabilities? Imprecise probabilities allow us to solve, partially at least, those issues without incurring in exponential complexity. So, a few remarks about the theory of imprecise probabilities. The ground of this theory is the moves from notice that epistemic subjects are not always in the position to assign a precise probability to all the events, but their beliefs impose some constraints on these probabilities, which means that there exist probability distributions that are compatible with those constraints and distributions that are not. So the idea behind the theory of imprecise probability is that we replace the standard precise probability distributions, such as the transition probability distributions, with a family of probability distributions compatible with constraints defined by the beliefs of a subject. In practice, in the mathematical sense, we do these operations introducing Credal sets. What are Credal sets? So a Credal set is a set of probability distributions defined over values of our space of states and closed under given constraint. We can visualize a Credal set, as you see in this representation, as a cone, or maybe as the intersection between a cone and a simplex of probability. Okay. As you can see here, if we visualize the simplex of probability in a sample space with 3 elements, a standard probability value is a point, whereas a Credal set is a set of points. The interesting property of Credal sets, that is the properties that allow us to compute inferences in polynomial time, as I'm going to explain later, is that a Credal set is fully specified by its finite set of extreme points. So here we obtain, for instance, a full specification of the Credal sets, taking the 3 extreme points delimiting the Credal set. Okay? Okay. So for what concerns our model, we use conditional Credal set, and in particular, what is a conditional Credal set? Is a set of conditional probability distributions closed by given constraints. Using conditional Credal sets, we can define an imprecise transition matrix that is a transition matrix describing the stochastic behavior of our system, but that is not composed by precise values, but by Credal sets. And in particular, each row of our matrix is a conditional Credal set. Okay? In such a way, we can model computational systems where stochastic behavior is not stationary. And in particular, we can model systems characterized by transition probabilities that vary across time within the borders of the Credal sets included in the imprecise transition matrix. Okay? So, using this new imprecise transition matrix made of Credal sets, we can introduce a new structure that is the imprecise counterpart of probabilistic interpreted systems, and is called imprecise probabilistic interpreted system, of course. What is an imprecise probabilistic interpreted system? Is a tuple composed by a finite and empty set of states, a finite and empty set of agents, and instead of having a single transition matrix, we have a family of imprecise transition matrices that describes the non-stationary stochastic behavior of the single agents in the system. Of course, we have a family of epistemic equilibrium relations, set of labels, and a labeling function. Okay. Now the overall stochastic behavior of the system is described as a global imprecise transition matrix, okay, where the rows of this matrix are joint conditional Credal sets that can be obtained by those of single agents. Okay, so we have an operation to obtain new a global transition matrix as we do in the previous case, but this time this matrix is made by Credal sets. Okay. Now we have introduced these new kind of models that are the imprecise counterparts of the standard probabilistic interpreted systems, and over these models we introduce our new language a new language that we call EIPCTL, epistemic imprecise PCTL. This is an extension of standard PCTL where and is analogous to PCTLK, but instead of having the standard usual single probabilistic operator, we have these three probabilistic operators, one to represent intervals of probability, one to represent lower bound of a probability, and one to represent an upper bound of a probability. Okay? So to represent borders of Credal sets, in fact. We have also introduced two new operators to represent imprecise probabilistic beliefs, was meaning, I will clarify following. Let me go quite briefly. The semantics is analogous to those for standard PCTL, with the only difference that we replace the precise probability operator with lower and upper bounds. Okay, so bounds of the Credal sets. Okay, the interesting things is that we can compute relevant inferences that are computable in standard Markov chains, also in imprecise probabilistic interpreted systems, without increasing the computational complexity. And this can be done using these two transitions operators that are transitions operators that compute, that apply to each real valued function of the set of states. Okay, we have a lower and an upper transitions operator that are defined in this way. And the interesting thing is that each application of one of these two transitions operators is in fact an optimization task that can be solved through linear programming in time of polynomial in the number of states of the model. And this is the K element that allows us to compute inferences. So we go directly to the interesting inferences that are the inferences arising with it probability, and that, as I mentioned, it can be used to compute bounded until and until operators in the scope of the probabilistic operator. So again, here, instead of computing the standard usual precise it probability, we compute the lower and upper bounds of it probability, and these lower and upper bounds can be computed through this procedure. It is a recursive procedure defined over increasing values of time. Here we have these two vectors that represent indicator vectors. So this is the indicator vector of A that has value 1 for each state in the event A and 0 otherwise. The indicator vector of the complement of A and the transitions operators. Okay. Iterating over increasing values of tau, we can compute both the time-bounded it probability, but also the standard it probability. How we compute the standard it probability? Simply iterating this schema over increasing values of tau until convergence. This is possible because it has been proved that for both these two scheme, the limit for tau to infinite corresponds to the fixed point of these algorithms. Okay, so in this way we can compute the probability of interest. Here I put for simplicity just the upper bound, but is the same for the lower bound. The probabilities of interest can be computed here, as you see, as the it probability of this conditional event that corresponds to this schema, and the same schema can be used for unbounded until but using the limits, computing the limits to infinite that corresponds to the fixed point. Okay. For imprecise probabilistic semantics is the same operation, but considering one single agent instead of the whole global, the whole multi-agent systems. But I go quickly on this point as it's not really relevant. Okay, the last extension that we made, especially in the last work, concerns Markov reward models. Okay, until here we treated simple multi-agent systems, whose single agents behave as imprecise Markov chains. Here we want to model also agents that, shifting from a state to another state, obtain a reward. Okay, and this is a first step towards modeling so-called Markov decision processes, and also to reach a connection to it, for instance, fields connected to Markov decision processes such as reinforcement learning and so on. So, for obtaining our extension with rewards, we consider a new kind of models that are Markov reward models. We have the standard, usual, precise version of Markov reward models, where a Markov reward model is a pair composed by a Markov chain and a reward function that assigns to each state of the model a natural number representing the reward or the cost, as you prefer, that the agent earns passing through the state. Okay, interesting. We can really, in a real simple way, obtain the imprecise counterpart of Markov reward model that are imprecise Markov reward models, where instead of having a standard Markov chain, we replace the Markov chain with an imprecise Markov chain. We have a pair of imprecise Markov chain and a reward function. So an imprecise Markov chain with a transition matrix that is made by Credal sets, as I said. Okay, following this path, we obtain also imprecise probabilistic interpreted systems with rewards. What is an imprecise probabilistic interpreted system with rewards? Is a pair composed by an imprecise probabilistic interpreted system and a reward function that assigns a natural reward to each state in the system. Okay. On imprecise probabilistic interpreted system with rewards, we define a final language that is a further extension of the EIPCTL already introduced, and it's called EIPRCTL. So EIPCTL with rewards, basically. The syntax is the same of standard PCTL, of standard EIPCTL introduced before, with, in addition, this new phi and psi formula. We have a formula to represent the lower and upper bounds of expected cumulative reward, and we have a psi formula to represent what is called reward-bounded reachability. What is the meaning of this formula? So these two formulae means respectively the lower, the upper bound of the expected cumulative reward earned by the system until reaching a state that satisfies phi is s equal greater than r, where r is a specification of a reward. Of course, we have again a formula to represent the interval of rewards. And finally, the psi formula has this meaning: phi1 holds along the path until a cumulative reward equals to r is earned, then phi2 holds. This is an analogous of the time-bounded reachability modeled by the time-bounded until operator, where instead of having a bound given by the time, we have a bound given by a reward. Okay, the semantics connect, so the satisfiability conditions connect the meaning of this formula with usual inferences that can be computed in imprecise probabilistic interpreted systems with rewards that are inferences concerning the lower and the upper bounds of the expected cumulative reward of reaching the event sat phi, so the event made by all the states that satisfy formula phi. And our final task, is to compute the inferences in a feasible way, namely in time polynomial in the number of states in the model. We apply the same algorithm before, and we define, okay, here we have the semantics for word-bounded reachability. Okay, the interesting things that we discover that we can use procedures analogous to those that we introduced for lower and upper bounds of eating probability, also for computing expected cumulative reward. And in particular, we have this procedure that allows us to compute the expected cumulative reward by iteration of increasing values of tau, where the lower, respectively upper bound of the expected cumulative reward at time t of reaching event sat phi is given by the vector of reward plus the indicator vector of the complement at sat phi that multiplies the transition operators applied to this new function that is not the eating probability, but to the expected cumulative reward at time step, preceding time step. Okay, so this is an iteration. Again, it's possible to prove that the unbounded version corresponds to the fixed point of the time-bounded version, and thence that this value can be computed iterating the schema of increasing values of t until convergence. The same with probabilistic inferences that involve this new kind of psi formula. Also here I skip the details. We can provide again an iteration that is that involves transition operators, and again this iteration allows us to compute. This time is an iteration not only over increasing values of t, but also over increasing values of this value rho that represents reward. So we iterate over times and over rewards. And at the end, we obtain a feasible procedure that compute lower and upper bounds of this probability that include reward-bounded formula. Okay, all the technical details, of course, are provided in the paper. I have not the time to enter really in the details, also because they are quite maybe too technical for being explained in a few time. So I want to go to conclusions, mentioning the advantages of using imprecise probabilities. The advantages are that we can do all the standard model checking tasks with epistemic stochastic multi-agent systems that we do in standard precise probabilistic model checking. But using imprecise probability, we can model non-stationarity, stochastic agents, whose transmission probabilities vary across time within the borders of the Credal sets. We can also model high order uncertainty about probabilities, because the values of probabilities have not to be precisely specified. We can have intervals or Credal sets. And finally, compared to other formalism used to model non-stationary stochastic agents and high order uncertainty, this time the formalism of imprecise probabilities allow us to compute all the relevant model checking tasks without increasing the computational complexity that remains polynomial in the number of states of the model. Okay, this is all, and thank you everyone for the attention. And you can see more details about this research on my website, where there are reported 2 versions already published of this work, and in the future we hope also the final paper we submitted 1 month ago. Okay, thank you everyone.
Thanks, Alberto.